Yes, the session is now recording. So, once again, welcome everyone to the weekly problem solving session for the NPTEL course titled Physics of Nanoscale Devices. I'm Jyotishwaran. I'm a PhD student from the Department of Electronics and Communication Engineering, IIT Roorkee. So, while I'm beginning today's session, for the people who are attending live, if you have any questions from the previous week's or even this week's content, you are free to ask them during this session. So, if you have any questions, just go ahead and unmute yourself and ask the question, or you can also do the same in the chat. So, yeah, all right. So, l- I'll continue with the session. If there are any questions or queries, please feel free to ask. So in today's session, we are only going to be discussing two topics, and mostly we are going to explore them by solving the actual, problems associated with the topics. So the topics for this week are density of states and the Fermi Dirac distribution. So these two ideas, they form the foundation of the behavior of electrons in solid, along with quantum mechanics, of course. So these two over here, essentially, yeah, let me just, so they form the foundations of electronic behavior. So if I know what kind of structure my solid has, and if I can derive the density of states, that in combination with the Fermi-Dirac statistics will be able to tell me what kind of a behavior, electronic behavior the solid will have under different conditions. It will tell us if the solid is going to be a conductor, an insulator, or a semiconductor, or if we move further deeper into things with a little bit more quantum mechanics, we can even search for novel behavior. We can look for, like, this is essentially the starting point for studying even advanced physical properties such as, topological properties associated with electron conduction. Is there any spin dependence? Is there, other weird properties that arise from the structures? All of those things begin from density of states and Fermi Dirac distribution. So when I'm talking about density of states, I am talking about the, like, as far as problems go, the courses go, we shall concern ourselves with 0, 1, 2, and 3 dimensional solids. So these are the four things that we shall be looking at, and of course we'll be looking at the Fermi Dirac distribution in the latter half of today's session. So before I begin the session in earnest, I noticed that there were a bunch of questions on the forum. So I shall be addressing those questions one by one during the course of this session as well. So I don't think the person who posted the question has joined us today. So hopefully when they watch the problem solving session, they'll have their questions answered. Okay. So first we are talking about density of states. Density of states is a density function. So what is a density function? Remember, it is the same thing that we have from, it plays a similar role to the square of the magnitude of a wave function in quantum mechanics. Essentially, this mod psi squared x is the probability density function from our first two sessions. Density function. So similarly, this density of states is a density function. DOS, typically this is denoted by the symbol D of E. So D of E is a density function, and it represents the number of energy states a quantum system has between energy E to E plus DE, just like what we saw in the case of the probability density function. It is the probability of finding the particle between position coordinates x to x plus dx. So one should not just look at the value of the density function and say, oh yeah, this is how many states I have. No, we are supposed to integrate over an interval. And the spacing between these quantized, like typically, not typically, like by now we know that if I have a confined system, then there is going to be energy quantization. So when we talk about solids, of course we are talking about confined solids because solids are, finite in size. Like I cannot have an infinite solid that spreads all through the universe. So of course they are confined materials, and in that the energy spacing between these confined these quantized energy levels depends on the size of the system, and increasing the size of the system essentially decreases the spacing between these energy levels. So let us see what each of these statements mean. So yeah, I will also write this. So n of e, this is the number of energy states. I mean, N may not be the right symbol to use. What shall I call it? Uh, you know what? I used N last time, so I will use this time N this time also. So essentially, what we have is N of E, or more precisely, D N of E is equal to D of E dE. So where N of E is the number of states at energy. So N of E is the number of states at energy. Okay. Okay. So let us proceed to the next slide. Yeah. So first, we'll start from what we know. So what have we discussed until in the first 2 weeks of this course? We have seen how to solve the Schrodinger equation for some limited collection of systems. We've seen a little bit about the Bloch's theorem, the chronic Penny model. So in every, like as we progress through this session, we'll try to use only those ideas to derive these concepts. I would also like to point out that the method I shall be using to derive the density of states will be slightly different from what is done in the lectures. So, it is an alternate method, and, hopefully it will be of interest to some people. Okay, so first we need to consider an infinite 1D square well and calculate the following quantities. So here again, I will not be solving the Schrodinger equation. I am going to assume that we all uh, know how to solve the Schrodinger equation, at least for a square well. So layout, blank, yes. So let us start with 1A. Let me see if I can reduce the thickness slightly. Yes. Yeah, so, oh no, I took it to problem 2. Yes. Yeah. So 1A. First, the difference between two consecutive energy levels in the system. So first, I know En for a particle in an infinite well is given by n squared n square h square, or rather, yeah, sorry. Let me write it in terms of h bar squared. So this is n squared pi squared h bar squared divided by 2na squared. So this is the energy level where n is equal to 1, 2, 3, and so on. So essentially positive integers. So yeah. So we need to find the difference between the consecutive energy levels. This implies En plus 1 is going to be nothing but n plus 1 whole squared pi squared h bar squared divided by 2n squared. So alternatively, what I can do is I can observe that n is the only quantity that varies as I move from one energy state to the next. So I can in general say that En is equal to n squared E naught, where E naught, which is the ground state energy of the system, is given by pi squared h bar squared divided by 2m E squared. So E1, like the ground state energy, is going to be E naught, E2 is going to be 4 times E naught, E3 is going to be 9 times E naught, and so on and so forth. So what is the difference between, oh, yeah, I should have written as En plus 1. Oh, yeah, En plus 1. Yes. So now what is En plus 1? And since we know this, we know that En plus 1, first I can say this, En plus 1 is greater than En, most certainly. Yeah. And this is also kind of obvious. It's very rare. There are cases, but we are not looking at them now, where I will start numbering my energy levels from the highest and move down as the index increases, as the counting index increases. But here, I'm just pointing this out that En plus 1 is greater than En. Now, therefore, En plus 1 minus n plus 1 minus En is nothing but n plus 1 the whole squared minus n squared multiplied by E naught. And this comes out to be 2n plus 1 E naught. All right. So this is the quantity. If I want to write the exact value, this is 2n plus 1 into pi squared h bar squared divided by 2n a squared. So this is part A. Now what is part B? Explain the variation of the above derived quantity at higher energy levels. So let us move to part B. So what happens as n increases? So we know, and let me call this, so let me say this quantity, I'm going to call it as, I'm going to call this as delta n. Okay. Should I call it delta n, or let me say it's delta n plus 1, because n plus 1 is the higher energy level. So this is delta n plus 1. This is essentially the energy difference. Now, first thing we can say directly is delta n plus 1 increases with n. And secondly, increases linearly with n. We can also see that, like if I were to plot if I were to plot the variation of delta n versus n, then I know that this will kind of be, of course, it is never going to be 0 because there is a 1 here. So it will start kind of over here and raise as a straight line. So this is, and this point is going to be E naught. So this is what I mean by linear increase. And secondly, obviously, as we can see from this graph, limit n tending to infinity of delta n is equal to infinity, which implies as n increases, the difference between consecutive energy levels keeps increasing. It becomes larger and larger and larger. So at very high levels, very high energies, not very high levels, I mean they are interchangeable, spacing between two energy levels is very large. So this is part B done. Now what is part C? In part C, we've been asked to find out. I mean, technically, I'm the person. Wait, what happened to my pointer? Here I am. Yes. So in part C, we need to. I'm claiming that I can use this relation to find out the density of states. So let us see how we can do that. So use the above function to obtain the density of states for a 1D system. So yeah, need to create a new slide. Yes. So now we come to 1C. Now, in the lectures, you would have done the derivation through going to the momentum space, looking at the k space of the system, and then counting the k points, and that is the route you take to this derivation. However, here I'm saying this quantity delta n is going to tell me how to derive the density of states. Now, how is that going to be possible? So remember that. Okay, yeah. So we can directly look at this. So this quantity right here, can you see a relation between En and delta n or delta n plus 1? So point is, I will write this here. If you have any doubts, please ask me. I can say delta n plus 1. In fact, I shouldn't have called it n plus 1. I should only call it delta n. And now I realize the error. Because if I write this as delta n plus 1, then I cannot calculate this for the ground state. Yeah, so this is delta n. I hope you can understand that. Had I written this as delta n plus 1, then for n equal to 0, I will not have any E0 because the lowest possible energy state is E1, the ground state energy. So yeah, it should be delta n. Yeah, so delta n, not delta n plus 1 over here, uh, is equal to den by n. Sorry, dn, not d, by dn. I hope you can see that because En is n squared e naught and delta n is 2n plus 1 e naught plus e naught. So when I do d by dn of this, n square will become 2n. I'm just adding an e naught to that. So that gives me the spacing between two energy levels. Now remember the definition. It represents the number of energy states a quantum system has from E to E plus dE. So this essentially tells me that if I look at a finite window, essentially what I'm saying is, if I'm looking at the use a different color. If I am looking at the energy levels like this, yes. So this is not a graph. I'm just drawing this. So if I say the ground state energy is E naught, the second is over here 4 E naught, and then I have double of that more or less. So 9 E naught. Essentially, what I'm asking is if I take a window, if I take a small window here, then in this window, DE, how many states are there? And as I keep increasing E, keeping this window size the same, how many energy states am I likely to find? So that is, so D of E is number of energy states that are inside the window Now I know that the energy spacing is there. So like technically I cannot make D very small. If I need to catch at least uh, one energy state inside this window, then my window should keep growing larger and larger and larger. And by how much larger should it grow? It should grow this large. So at ground state, I can set n equal to 0. So I need a window that is at least of width E naught. As I go to the second energy state, I will need a window that is at least 3 E naught starting from E naught. So as I'm moving this, my window needs to become bigger and bigger and bigger to capture at least one state. Because as pointed out here, as the energy increases, the spacing between them also increases. So yes. Now using this, we can now I will show how this can be related to the density of states. Now density of states. Oh, sorry. Density of states can alternatively be written as. So essentially, what do I say when I mean the density of a certain like if I have a mass? What do I mean when I say when I try to denote its density, when I'm talking about the mass density or the charge carrier density, I'm defining a small area or a volume and I'm asking how much mass or how much charge is present inside this area or volume. Like that, what do I mean when I said, like, of course, here I've written one definition. So density of states alternatively can be asked as how many. So let me, I mean, I'll be repeating the same thing over and over again. So instead, yes, alternatively, I can do this. Yeah. So I know E is equal to n squared E naught, which implies n is equal to E by E naught, whole power 1 by 2. I hope this is okay with everyone, which implies delta n is going to be 2n, oh sorry, 2 into, yeah, E by E naught whole power half plus, oh, 1 into E naught. So this, what I've done is, yeah, like just remember this definition, ignore what I previously said. I was trying to move ahead a few steps. So I can just use this, get the relation between n, and then, because if I'm asking what is my n value at a certain energy, this is how I will calculate it. So, and yes, so now the entire equation delta n is written in terms of like constant parameters. E naught is a constant that depends on the size of the system, and E is the energy at which I would like to probe. So essentially now delta n, I've kind of eliminated n, so I can write this as delta of E. So essentially because I've eliminated the n dependence here, so I can write this as 2 times square root of E upon E naught plus 1 times E naught. Now what I'm telling, I will come back to this in the second question. D of E D 1D of E, the 1D density of states is the delta of E by D. This is the derivation definition that I am giving. So from this, what I have to do is I need to take the derivative of this with respect to E. Now that is going to be 2 times. So I have square root of E over here. So that is going to be another 2 times, yes, Oh no, let me write this as e to the power minus half. Yes, e to the power minus half. The one when I'm taking the derivative, it does not depend on e. So this is going to be this divided by square root of e naught. So this is e to the power half. So this will give me 2n, 2 into 2, e to the power minus half, e to the power minus half into e naught to the power half. Now if I substitute the values, so this is going to be 4, let's see. So this is going to be 4 e to the power half into square root of e naught is going to be square root of pi squared h bar squared by 2m a squared, and this is going to be, oh, oh no, 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 no. I shouldn't have written equal to here. D is proportional to this. Yes. It's not an equality yet. There is one more factor that I will bring in. So this is, yes. So only root 2m will stay inside here. So now I can, and this is e to the power minus half. So I can write this as 4 into square root of 1 by 2me into just square root of this. This is going to be pi h bar, oh, not square, pi h bar by a. Yes. So let me go back here and add that for those who will only read the slides, a is width of the well. Yeah. So a is width of the well. So this, yes. And now 4 is 2 squared. I can essentially write this as 2 root 2. So this is going to be 2 into square root of 2 upon me. Pi h bar is essentially going to be h by 2. But you know what? I will leave it as that. Am I right? Yes, I'm right. Oops. Sorry. Just 1 second. What have I asked in the second question? Yes. So you know what? I just realized that deriving it from this is a bit complicated. So what I'm going to do is I'm going to stop it here with an important message. Now, yeah. So from this, I definitely know d of e is proportional to e to the power minus half. So rather than deriving the density of states directly, first by using this method, here I have not done very much, like I have essentially only derived this quantity. I have derived this quantity over here, and from this we have arrived at this relation that somehow d of e, d1d of e is proportional to e to the power half. Now how do I arrive at the exact density of states relation? We shall look at it over here. So for that we need to go to problem 2. Now same again, we are back to a 1D square well. Now we need to plot the number of energy states found at or below a given energy level. So slide. Yes. So 2a. So number of energy states at or below E. So I know E is En is equal to n squared E naught. So question is, so number of states and oh, let me see, energy and number of states. Let me try to plot, not plot, just tabulate these two values. So first, how many energy states will we have below E naught, at or below E naught? At or below E naught. So E naught is the ground state energy. There cannot be an energy level below that. So it is 1. Number of states below E naught is definitely 0. Next energy level is 4 E naught. So at 4 E naught, I will have the first excited state, the second energy state, and the ground state itself. So this is 2. Then at 9 E naught is going to be 3. And then I will have 16 E naught. There will be 4 energy states at or below this value. So if I were to try to plot this as a graph, like part B involves finding the function. So, A and B kind of go together. So let me look at this graph. Yeah. So this is, and let me call this quantity, uh, what shall I call this quantity? Because I call this, yeah, why not? I will call this quantity here, number of states, I'm going to call this N of E. Okay, number of states. So this I'm going to denote as N of E. So to put it in more like precise terms, N of E is the, oh, you're going to see it. Like I will like plot this and then tell you what we have done. I don't know what. Yeah, so this is N of E, and over here this is E, and I have E naught, 4 E naught, 9 is going to be 4.5, so it's going to be 1, 2, 3, 4 over here. Yeah. So below E naught, I know this quantity is 0. There are no energy states below E naught. And let me say these are the ticks over here. So this is going to be 1, 2. There is a reason why I'm trying to draw this graph as precisely as possible. So this point here is going to be, so this is going to be, so this is E, let me say I'm writing this as E by E naught. Okay. So this is E by E naught. So this is going to be 1, 2, 3 is going to be somewhere in the middle. Then I have 4, 5, 6, 7, 8, 9, and so on. So I will have 10, 11, 12. Unfortunately, I didn't draw the line long enough to be 16. Like it will go to the end of the page. But 3 points, like I also have the 0 point, so it's kind of okay. So when n goes to 1, I will have my number of states at or below is going to be 1. Then at this equal to 4, this is going to be here. And at 9, we are going to reach 3. So the graph is going to look something like this. Not something like this. If plotted correctly, it is going to look like this. You know what? Rather than trying to fit this, I will just make this dot bigger. Yeah. So this is how the graph goes. As I keep increasing in E, this is increasing, but mind you, this is not increasing linearly. A straight line would be like this. This is actually increasing sublinearly. So this is sublinear. So this graph, you say it shows a sublinear increase. Essentially, its rate of increase is less than linear rate. Okay, so now part B is to find the function. Like essentially, I need to fit a curve over here. And the curve, I hope you can see it. At 1 it is 1, at 4 it is 2, at 9 it is 3. So essentially, let me just move over to the next slide. Essentially, n of e is square root of e by e naught. I hope that is clear now. N of e is square root of e by e naught. In fact, not in fact. So n of e is square root of e by e naught. But this is also not correct because if I include spin, like if we are talking about electrons, including the spin of electrons, n of e is equal to twice square root of e by e naught. Now, but this graph is only for integer values. Essentially, this is not a continuous graph. This is a pointwise graph. So what we have to do first is consider. Now remember, delta E or delta N was equal to 2n plus 1 into E naught. Now consider the limit where A tends to infinity. That is, the well is infinitely wide. And this is exactly the system that we are describing, because see, over here, uh, yes, I'm talking about a 1D system. So what do I mean by a 1D system? Essentially, when we are counting the density of states, we are not considering the potential. We want to find out what is the density of states when I have a free particle roaming in one dimension. So to get that, I need to make my well as wide as possible. So in that limit, what you will see is that this quantity E naught will become as small as possible. So delta n will actually tend to 0. But what we need to observe is even if it tends to 0, as n increases, delta n will still keep increasing. So even though the value for like this E naught becomes 0, I shouldn't say delta n tends to 0. That is the wrong thing to say. As A tends to 0, E naught becomes A tends to infinity, E naught becomes very small. So in that case, if I were to write this graph as just E, then I will notice that these points, as A becomes larger and larger, these points will start becoming closer and closer and closer. In that limit, in the limit A tending to infinity, this graph will become a continuous graph, and that graph will have this function, square root of 2e by e naught. So now I will be able to confidently tell you that. Now remember what I had written in the. Now I'll go back to the intro slide. Oh, this is the questions. Yes. So remember, I told you the spacing between the quantized energy states of a system depends on its size. So the larger I make my system, the smaller the spacing becomes for the case of a 1D system. And yes, that is what is written here. And I wrote dn of E is equal to d of E times dE. So I had essentially given the answer in the first slide itself. So this would imply d of E is equal to dn of E by d. So I just need to take the slope of this quantity here. Therefore, d of E is equal to 2 into, yeah, now I can write this 1 by square root of E naught into 2 by square root of E, which is the derivative. Now this 2 is because of the electronic spin. Each energy state can take 2 electrons. Now why that is so? Well, we are not going into the definitions of it. We assume that we all know some basic atomic physics. So this is 2 electrons per state. Okay. So yeah. And yes, so now this I can write. I'll move to the next slide to make things clearer. So now d of E or d1 d of E. Oh, no, I should write it as only d of E now. I shouldn't call it d1 d of E. D1 d of E is a different quantity. Okay, so this is going to be now 2 into 4 into 1 by square root of E naught into 1 by E to the power half. And square root of E naught I know to be, so this is 4 into square root of 2m into A divided by pi h bar 1 by E to the power half. Why did I put a semicolon there? Which is equal to 4 into A, 4. See, this is 4A by pi h bar into square root of 2m by E. Body. And now what I will ask is, so this is at some width A. Now I need to find out how much this density will change as the width of the well increases also. So that is the true density of, that is the quantity that I am interested in. So d1 d of E is actually d of E by A. So that is going to be 4 by h bar. I've written everything correctly here. Let me just check for the constants. Oh God. Yeah, I made one mistake. This is not 2 here, this is 1 by 2. And I think that was the mistake I made here also. Yes. Yes. It should be 1 by 2. So this is, no, 1 by 2 and 1 by 2 will cancel each other. So here it's going to be e to the power half. So nothing here. So yeah, 1 by 2 me by pi h a. So I'll arrive at a similar looking quantity here. So there is no 4 here. I apologize for the mistake, and I would have also appreciated if someone had pointed that out to me. So, yeah, and never mind. The mistake has been identified and the correction has been made. So, the 2 and half will cancel. Yes. So d by a, which is 1 by pi h, and yes, yeah. Now there is one more factor that we need to include here. That is, remember when I started counting the energy states, I said there were two states per spin. So the actual density of states, like when I'm counting the density of states, I want to, like, there will appear a factor of 2 here. Now how do I account for the, like, okay, now the actual d1d of e that you might have derived in the class will look like this. So d1d of e from lectures is 1 upon pi h bar square root of m divided by 2e. So you'll see that the d1d that I have derived is having an extra factor of 2. That extra factor of 2 arrives because we have a essentially, yes. So when I'm counting the number of, like, 2 electrons per state, but the truth is I have only one state, and this error happens to occur only in the 1D system, and so this is like double the value of the, and depending on where you read from, both of these expressions will be given as the density of states. However, for our purposes, we will be using this, but you can see that the relationship between this and this is off by a factor of 2. But the energy dependence, that d1d of e is proportional to e to the power minus half, not e. 2. But the takeaway message is d1d of e is proportional to e to the power minus half. Yeah. And that still remains. Okay. So, yeah. So, as you can see now, instead of going to the K space and deriving the density of states, we can actually look at the variation of energy, like the variation of the energy levels, take their cumulative distribution and take their derivative to get the density of states. Now, the third problem that we shall be looking at is repeat the previous, like, part A, essentially finding the number of energy states found at or below a given energy level for a 0D, 2D, and a 3D system. So, what I'm going to do is I'm going to do a 2D system first, then I'm going to do a 3D system, then I'm going to talk about a 0D system. So, and while going through these, I will also talk about what do I mean by a 2D, 3D, and a 0D system. Okay, so let us begin with yes. So part one, we shall talk about a 2D system. So I hope you are all familiar with the derivation of energy for a 2D infinite well. If you have any doubts, please let me know. So a 2D system. So I know energy E for a 2D square well is given by nx squared plus ny squared nx squared plus ny squared into E naught. Again, the E naught is, well, I'm assuming it's a square well, so length equal to breadth. Okay. I don't want to look at the general case yet. breadth or width. So this is going to be essentially what I mean is my 2D well is going to be like this. It's going to have length and breadth both to be A. So E naught is equal to pi squared h bar squared by 2 divided by 2m A squared. So yes, and of course nx and ny and nx comma ny are 1, 2, 3 and so on. Now as you can see, E the ground state, so E11 is equal to square root of 2 E naught. So right away there is one thing that you can notice. The more I increase the dimensionality of the system, the higher the minimum energy of that system is. If you can go back to think back to the first week's session, I spoke about the minimum energy a particle can have in a system. And we found out that for a 1D system, it was, like somewhere in the milli electron volts if you consider the particle to be an electron and the confinement to be around like 5 nanometers. Now, if I consider everything to be the same and increase the dimensionality of the system from 1 to 2, we can see quite readily that that energy also jumps up by almost a factor of 2. So the more degrees of freedom I give my electron, like the more dimensions I give it to move in, the minimum energy it requires to stay increases. And that is directly evident from the fact that now instead of one uncertainty relation between px and x, I need to do all the three uncertainty relations, py and y and pz and z also. So here, if I consider these to be the xy coordinates, then I need to consider the two Heisenberg uncertainty relations that gives rise to an increased ground state energy, an increased 0 point energy. Okay, and E12 is equal to square root of 5 E naught. Yeah, let me have this one at my side so that I can quickly calculate things also. Yeah, so yes. And coincidentally, since my length and width are the same, this is also equal to E21. And this feature, when two distinct energy states, now every energy state is uniquely identified by the nx value and the ny value. Now, if two distinct energy states end up having the same energy level, that is called, not two, in general, if more than one energy states have the same energy level, that is what we refer to as a degeneracy. So here, this is to be more precise, this is a twofold degeneracy. Essentially, there are two states with the same energy value. Okay, and then after this, I will have E 2 comma 2, and I mean there is only one way they can have that, and that will come out to be square root of 8 E naught. Yeah, and then I will have E 1 comma 3, which again is going to be equal to E 3 comma 1, which will come out to be oh no, why was I putting square roots? Square roots come later. I am really sorry. Yeah, so it's just going to be 2 E naught, 5 E naught, 8 E naught. I'm really sorry. Yeah, so this is going to be 10 E naught, and then I shall consider 2, 3, 3 comma 2. This will be 13 E naught, and then 1, 3 is done, 3, 1 is done, and then 1, 3, 3, 1, 2, 3, and then I will go to 3 and 3, correct? Yes. And finally, but Okay, yeah, let me just append that also. E33 is going to be 18 E naught. So how does this curve look like? So now I'm directly just writing E by E naught over here. I'm no longer concerned with the actual energy value. So the x-axis is E by E naught, and again I'm trying to plot N of E. So below E equal to 2 E naught, I have nothing. So let me say this is, yeah, 1, 2, 3%. I can do more than that. Let me scale this graph accordingly. So this is going to be 1, 2, 3, and 4. So this is 4 E naught. Alternatively, I can do it like this. And yes. So these are the x-axis graduations. So I start from 0, 1, 2, 3, 4. Whoa, we have a new attendee joining us. Just 1 second. I'll use my mouse. Yes. So yes, 4, 5, 6, 7, 8. Yeah, I'm sorry, like 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20. So, of course, less than 2 E naught, and this is going to be, half and half. So, this is 2, 3, 4. Yeah. So, I'm going to call this 1, 2, 3, 4, 6. So, below 2 E naught, nothing is happening. At 2 E naught, I have one energy level. And once from there, I go to the next energy level, which is at 5 E naught. We have two energy levels. Then the next one is at 8 E naught. Now, notice that for the 1D case, this graph actually progressed very smoothly. Like I always took steps going to the next square number. I was at 1, at 4, at 9, and then 16, and so on. Now, the jumps are occurring rather irregularly. But it doesn't matter. You'll pretty soon see what is happening. So then at 8 E naught, we have, oh no, no, no. Yes, at 5 E naught, I have two states. So it is no longer at 2. At 5 E naught, it jumps to 3. I'm sorry. So at 5 E naught, it is going to go here. Then at 8 E naught, we have one more energy state. So we are at 4. Yeah, this line should be a bit lower. No, it's going to be here. Okay. And then after 8 E naught, we were at 13 E naught. Sorry, 10 E naught, where we added two more states. So 10 E naught, we went to 6. And then at 13 and 18. So what you can see is that this line is kind of wiggling up and down. But if you observe carefully, the graph is more or less, it is more or less a straight line. At some points it will be above the straight line, at some points it will be below the straight line. This is too steep. Yes, it's going to be like this. So this line is more or less straight. So this will tell me that n of E is actually proportional to E. And again, I will consider the case where A, like the length and the width of the well is tending to infinity. So the spacing between these points will become closer and closer and closer. And since n of E is proportional to E, I'm not going into the full derivation here. I can directly say d 2d of E, which is proportional to d n of E by d, will be proportional to e to the power 0. Since it is linear, when I take the derivative, the energy dependence vanishes. So by just considering the number of energy states that occur at or below a certain energy level, I can get an idea of how the density of states varies. Okay, now let us start the second part. So 2D is done. Now we are looking at 3D. Now in the 3D case, I will not draw this graph again because as you can see, I take or you know what, let us sketch the graph. Why am I refraining from that? So here I will quickly write the energy values. So E111. So I hope this notation is clear to all. Essentially, instead of nx square plus, why am I doing that? I'm writing everything, so let me write everything. I'm sorry. Yeah, so let me say E is equal to nx squared. Again, now this is a cubic well. Okay, instead of a square well, I have a cubic well. So length, breadth, and height are all uh, the same quantity A, and z squared times E naught. So the energy values, so E and number of states. So the energy levels, I will just write the nx, ny, and z value. So the ground state is going to be 111. The second excited state is going to be 1, 1, 2. And now we have a threefold degeneracy 2, 1, 1 and 1, 2, 1. The second excited state is going to be, so here we need to actually evaluate and find out which is larger, 122 or 113. So we can see that 122, when I square and add them, it comes out to be 9, and 113 of course is greater than 9. So I will have 1, 2, 2, and again 3 copies, so plus 2, and then I have 1, 1, 3, because 2 to 2 is 12, whereas 1, 1, 3 is just 11. So there is going to be plus 2 states. So here I have a threefold degeneracy. Yeah. Similarly, there is a threefold degeneracy here. And lastly, I will say the next highest energy level is going to be uh, next is going to be 1, 2, is over, 1, 3 is over. The next is going to be 2, 2, which will have 12 E naught. So what are the energy values? Over here it is 3 E naught. Over here it is 4, 6 E naught. Over here this is 9 E naught. And over here this is 11 E naught. And 2 to 2 is 12 E naught. Okay. So now Below 3 naught, there is of course nothing. So at 3 naught, I have one state. At 6 naught, we have 3 naught and 3 more states. So this is 4. Then at 9 naught, I have another 3 states adding. So that is going to be 7. And then at 11 naught, I have another 3 states, further 3 states adding. So that is 10. And at 12 naught, we have one more state adding. So that is 11. So how will this graph look like? So this graph is going to look like this. So I need to go from 1 through 11, right? Yes. So okay, my y-axis needs to be 1 through 11. So one take here, 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 and divide by 4. 8, 9, 10, 11. Yes. And over here, I need the energy values to go all the way to 12. And this time I have taken enough squares on the x-axis. 2, 3, 4, 5, 6. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So once again, I'm plotting E by E naught, and then I have N of E over here. So below 3 E naught, there is absolutely nothing. So at 3 E naught, I have one state. So the next energy is at 6 E naught, but over there I'm going to have to go to 1, 2, 3, 4 over here. And then at 9 E naught, we jump up by another 3. So 9 E naught, wait, where am I? At 9 E naught, we have to be at 4, 5, 6. This is slightly off. 7 will be more or less over here. So it will be here and yeah, like this. Has to be green. Yes. And then we have a further 3 more states adding at 11 E naught. So at 11 E naught, we will go to 7, 8, 9, 10. So over here. And at 12 E naught, we will have one more. So, oh no, this should be slightly and more or less correct. So this graph, if we try to trace this graph, what you will notice is that this actually grows faster than a straight line. Like as x increases, this rise is super linear. And again, if I do the interpolation and things, I will find out here that n of e is proportional to e to the power 3 by 2. Okay, so that implies dn of e by dt, not dt, de is going to be proportional to e to the power half, which implies d3d of e again will be proportional to e to the power 3 by 2. And in truth, like why am I doing all of this? In truth, if I want to find the density of states of some arbitrary system, some special system that I'm constructing, some what are those structures called? Uh, why am I forgetting this? So essentially, we can have special structures. Like I can construct, most devices are special structures. They are not exactly 1D, 2D or 3D systems. They are like, heterostructures. Yes, that is the word. So when I have heterostructures, I cannot derive density of states by going back to the K-space, because the K-space for heterostructures is not very well defined. So when we are considering heterostructures, which are used in most modern devices, this is what we will do. We will do some kind of spectral analysis, get the energy spread, like how many electrons, or how many, like essentially, yes, how many electrons I am observing at each energy level. Take that curve and take the derivative of that curve to get the density of states. That is how it is experimentally done. And that is the reason why I am also like taking the effort to show how this technique relates to the density of states. Oh, no, 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 no. I wrote it as 3 by 2. I'm sorry. It is not 3 by 2. It is 1 by 2. Yes. So now we know, at least without using too much mathematics, by just plotting graphs, we were able to say that d1d of e is e to the power minus half, d2d of e is independent of e to the power 0, and d3d of e is square root of e. And you can actually look at what's happening here. So the energy dependence was e to the power n of e was depending on, no, not this. N of e was depending on square root of e. If I increase one more dimension, I add another square root of e. So it becomes e to the power 1. If I add one more dimension, it becomes e to the power 3 by 2. One more square root of e. And when I'm taking the derivatives, the appropriate results start emerging. So these energy dependences on the density of states, they are not some magical quantity. Okay, so before going to the 0D system, let me take a brief detour. So let me say a few brief comments on the 1D density of states. 1D density of states. So if I were to plot the 1D density of states, it is of course 1 by square root of e. So it is going to look something like this. It's going to be like this. So, and this is d1d of e. So limit e tending to 0 of d of e is infinity. So what does this mean? Why am I saying that the density of states is infinite? Does that mean there are infinitely many energy states near zero energy? But over here, when I try to plot this graph, I clearly I'm mentioning that when I go to near zero energies, I have no states. So what is this implication here? Like it seems very counterintuitive, because in this graph, I'm clearly stating that there are no energy levels present below a certain energy. But when I plot the density of states, somehow the density becomes infinite. So how can I have infinite density with no energy states? The answer to that can be obtained by, and yeah, that is why I was keen on deriving this quantity right here on this common, this quantity right here. Now remember, delta n keeps increasing as E keeps increasing. So the infinite density of states implies that the closeness between two consecutive energy levels is maximum at lower energy levels. And no matter how large my infinite well is, my 1D square well is, as I keep increasing the energy, the closeness between these energy states decreases. Since the closeness decreases, the density decreases. So this infinite density of states that I'm seeing here is merely an indicator of the infinite. I mean, technically, I shouldn't say infinite, but you know what? I will write infinite. Like we need not be too mathematically precise here. The infinite DOS is merely an indicator of the closeness of the energy levels. So what is meant here is as E becomes lower and lower and lower, my energy states are more closely packed. As E becomes higher, the energy states are more like loosely packed, like they are farther and farther and farther apart. And to put a definitive, like, end to this confusion, I will write this relation between N of E and D of E alternatively. Like previously, I wrote this d to d of E or whatever density of states is proportional to dn of E by dE. Now I will say also this. N of E is equal to integral E min, which is the minimum energy of the system, to E d of E times t. So what we need to remember is the only relevant point of my density of states starts at the E min value. Anything less than the E min value, I don't have to care about because I know there are no energy states available over there. Like we have the laws of quantum mechanics to tell us that I don't even have to bother looking for energy states below that. And since E min can never be zero, like we have established that using the Heisenberg uncertainty principle, d1t of E will actually never truly be infinite for all meaningful purposes. Yes, it will be very large, but it will never diverge to infinity. For that, E has to tend to 0. Okay, so I hope this clears any doubts on the infinite value of density of states, because for a 2D and a 3D system, luckily, fortunately, we find that the density of states never actually diverges. It in fact stays finite at all times for all values of E. Okay, now with that brief comment done, let me do it for the 0D. Now, before beginning the 0D case, let us talk about what do I mean by the dimensionality of a system. So when I'm referring to, so again, one more brief detour. So what is the dimensionality of a system? At least for our discussions, I'm not trying to like in this course. Okay, so this is not a general global discussion. So what is the dimensionality of a system? So of course I can ask you, but you know what, I don't want to spend too much time. But would anybody like to comment on what the dimensionality of a system is in this course? We have some live attendees. Is anyone interested in making a comment or two? Well, it's okay. I'll continue talking. So now what do I mean? Essentially what I mean are two things. First, how many, or rather in how many directions. So this question splits into two parts. How many directions can my, or not my, can the electrons in the material move freely? So in how many directions can the electrons move freely? The second question is in how many directions, same statement, are the atoms of the solid ordered periodically. So these are the two questions I need to ask. In how many directions are my electron? This is the first question is more important than the second. But the second one and the first are almost always related, like because of course electrons come from the atoms. So of course in how many other directions I have atoms, those many directions I can expect the electrons to move. However, there are exceptions to that. So this is the more important question. Okay, so this question is more important. Okay, so yeah. So now consider a solid, like a macroscopic wire. Okay, yeah, there is one more thing that I need to say. Now, what do I mean by move freely? Yes. So now to define this first question, what do I mean by what is moving freely? What does move freely mean? What it essentially means is to move freely. Move freely implies no confinement. That is all. Now, we already know, now we know, or we have established confinement implies yes. So confinement implies quantization. Where am I? Yeah, here I am. Implies quantization. So now again, I cannot just flip this statement, but for most practical purposes, I can do it. No confinement oops, implies continuous energy levels. And having continuous energy levels is what I mean by move freely. When I say an electron can move freely, I imply so no confinement or uh, the electron may have any momentum, any momentum value. And if you notice, in all my previous derivations, I have been saying one thing. What is it that I've been saying? I have been saying that I will consider the limit where, you know, yeah, all the way back here, I was saying that I will consider the limit where a becomes infinite. Oh, I should actually go down here. I mentioned it most recently over here. Did I not? Oh, I didn't explicitly write it, but I've been saying it repeatedly. Like whenever we derive the density of states, we said that okay, now the size of the well becomes very large. When the size of the well becomes very large, what happens to the allowed momentum values? Essentially, when there is no confinement, so in a in an infinite well, a tending to infinity implies n pi by a, not pi, n pi by a, which is essentially the allowed, k values, and we know that k relates to the momentum. The allowed k values tends to 0, which implies like essentially n pi by a tends to 0. Yeah, I should not write n pi by a tends to 0. Pi by a tends to 0, which implies momentum values are continuous. Continuous. Okay. So this gives me an idea of the dimensionality. How many directions does the electron have continuous momentum? So all these cases that we had previously considered are in a sense approximations, but they convey the right spirit. Okay. So momentum values are continuous, and this is what I mean by the dimensionality of a system. So when I'm talking about a 1D system, so when I say I have a 1D system, it implies free movement in one dimension. And these systems, one dimension. And these systems are, your nanowires and yeah, it's mostly nanowires because there are also some, single atom arrays, but they are also effectively modeled as nanowires. And truth be told, if I have very long, very long normal wires, like classical bulk wires, if the length is extremely long, then actually we will start seeing similar, 1D system like behavior. In fact, how do I, if you observe the physics of say something like a transmission line, where I'm transmitting electricity from one point to another, which are like several miles or several kilometers apart, you will see that even there I will, instead of looking at the movement of electrons as particles, I will look at the electromagnetic wave transmission through them. So the wave picture will enter, and we will actually be treating them not too differently from how we are treating our nanowires. And the scaling of current with voltage is no longer linear. There are other wave-like factors over there, and multiple other features start entering. So this 1D behavior, because what happens, of course, those transmission lines are pretty thick. They are not 1D objects, they are 3D objects, but in one direction they are extremely large when compared to the other two dimensions. So, very long conductors also show a similar behavior, although it is not fully quantum mechanical. In fact, it tends to be more classical. So, very long conductors, but nonetheless, the principle still holds. Now, what are 2D systems? Now, 2D systems are where I have free movement in free movement in two dimensions, and these systems, as we know, are most 2D materials. So I have 2D materials. And so we have 2D materials, and so 2D materials, what are them? Most famously known are graphene. Graphene is nothing but a single layer of graphite. Now, there was a question in the forums about why is graphene a 2D material? Because while graphite exists as a 3D, solid, the reason is the bonds in two directions. Like let me say the 2D, the sheet is in the XY plane and they are stacked along the Z axis. Essentially, I'm considering a solid like this. So I have, so I have a sheet like this, and I have several such sheets stacked on top of each other. Okay, so effectively this is a 3D object, but the bonds between these two layers, or any two subsequent layers in the vertical direction, are weak. So the green lines are weak bonds, and say when compared to the bonds in this direction and this direction, the x and y direction. So these are strong bonds. So what do I mean by strong and weak bonds? Essentially, the atom-atom attraction, the interatomic attraction is significantly stronger in the xy plane. Since the interatomic attraction is significantly stronger, the interatomic bonds are significantly stronger, the electrons can hop from one atom to another very easily. You can think of the bonds as, bridges connecting the atoms. Not an accurate picture, but, for conceptual purposes, it works. Those connections are very weak in the z direction. So, although the electrons can move in the z direction, when we consider something like graphite, it is not so free as in the xy direction. And this can be experimentally observed by looking at the resistance, like longitudinal and transverse resistance of the, even materials like graphite. If I try to pass current through, and if I have like fully like layered graphite, and if I try to pass a current through the sheets, the resistance will be higher than passing a current along the surface. So graphene is one example. Another commonly and these days discussed material is molybdenum disulfide, or any other transition metal dichalcogenides, where like I replace sulfides by oxides, tellurides, selenides, and things like that. So but again, we are not in a materials course, so we shall not discuss these things. Another very curious situation are interface layers. What are interface layers? Essentially, when I have a metal semiconductor junction, so when I have a metal semiconductor junction or an insulator semiconductor junction, so heterojunctions essentially. So what are interface layers? So when I have heterojunctions, where two different materials are kind of connected, not two different dopings, but two different materials altogether, like silicon oxide and silicon, or some kind of highly like some metallic silicon and semiconducting silicon. When I have heterojunctions, then at the layer our electrons will have only two dimensions of free motion, because when I have a junction kind of forming, see a junction forming, across the junction there will be a lot of inhibitions to the transport. We will see how this 2D material, like 2D motion kind of emerges even in a bulk MOSFET when we go into like week 7 or 8 of this course, where we shall look at the MOSFET properties. So even there, even in like our classical bulk MOSFETs, the conduction is effectively two-dimensional. We don't have a 3D current, we have a surface current flowing. And a 3D system, of course, it has movement in all three spatial directions. So what is a 0D system? Okay, now let me return. And 3D systems are, free movement in all directions. In all directions. And for this, we have like abundant examples, so we shall not discuss too much about this. Now, what is a 0D system? Now, again, like after the half an hour detour, I come back and ask, what is a 0D system? A 0D system is effectively a system where I cannot move my electrons freely. My electrons can only jump from one place to another, they cannot continuously flow. So, 0D systems are not here. Electrons are fully confined. And there are many ways of doing this these days. So if I'm talking about like conventional systems, I can have you know quantum dots. If I'm moving into superconductors, I can construct what are called Cooper pair boxes, where I will have two electrons confined inside of them instead of one. And there are many systems these days, like like every day new, what to say, like structures are being constructed. But the key thing to notice here is the electrons, while in that system, do not have free movement. They are completely bound, are fully confined or bound. And where do we have fully bound electrons found in nature? We find them in atoms. which is why 0D systems are also occasionally referred to as artificial atoms, which implies the energy here is fully discretized at all times. And there is no notion of size, because since the electrons are always confined in the volume, doubling the volume does not change anything because the electrons are still like fully confined in that volume. Like there is no notion of free movement. So in a 0D system, most common example are quantum dots, which have been around for like almost 30 years now. So we have only discrete energy levels. Energy levels. Okay, so now let us try to plot the NOV. Now coming back to the question that we started off with. So what is NOV for a 0D system? Dimension system. Essentially, since this is a 0D system, I'm going to have energies E1, E2, E3, and so on. The catch is I can never make these energies come closer. Like they're essentially what I'm saying here is E1 minus E2 or En minus, no, let me write it as, oh, so here the catch is delta n, which I introduced in the first question, is a constant. Delta n will never change in a 0D system because the notion of spatial scaling is kind of lost there. So now, if I want to plot the graph, how is it going to be? And I'm not going to talk about the uh, okay, so there is some auto straightening mechanism. I will have to learn how to do that. So yes, I have E1, E2, E3. I'm not saying they're equally spaced. Whatever, what? Let me. Why am I even implying that? Some E3 and then E4. There doesn't have to be a consistent energy spacing in general, although typically there is. Now, how is the thing going to look? N of E less than E1. Of course, there are no states available. Then there is exactly one state available after E1 to E2, and then there is there are two states available from E2 to E3, and then I will have three states from E3 to E4. So this is how my N of E will look. So N of E for a 0D system is equal to, now I'm writing a mathematical expression. I will explain what this is. E, or rather I should say EI less than E or less than equal to E, better, theta of E minus EI, where this function theta is the unit step function. So people who have studied some signal processing or done any other course in analysis or control theory and things like that will know this to be the unit step function, where theta of x is equal to 0 for x less than equal to 0 and 1 for x greater than 0. So whenever the argument is positive, the function will be 1. Whenever the argument is negative, function is going to be 0. So in fact, you know what? I don't even have to do this. I don't even need this thing. So I will just say sum over all values of EI, because the moment my E shifts to 0, it will come down to 0. Yes, sum over all EI. Yes. So I will just see how many energy levels I have crossed, and I will have that many states. Now, the density of states, d of E, is the derivative of this function, dn of E by dE. And the derivative of the theta function is what we saw last week. So d by dx of theta of x is the direct delta function, delta of x, which implies for a 2D, for a 0D system, d0d of E is equal to some summation of delta E minus EI, summation of EI. So this is how the density of states is. So the density of states for a 0D system is given by a series of unit impulses, a series of Dirac delta functions. If I'm including electron spin, there is going to be a factor of 2. And you would have seen some questions in your assignments to this effect. Now, how did we get the Dirac delta functions? This is how we got the Dirac delta functions. Like in this method of, because if I'm considering a 0D system, I can't even go to the K space. So the only legitimate way I have for calculating the density of states is this. I need to plot n of E and take its derivative. And we got the exact density of states function over here. And with this, we come to the end of our discussion on density of states. So the closer for today's session is the Fermi-Dirac distribution. There is not much to solve here, but a good deal to observe and understand. So the Fermi-Dirac distribution is the probability distribution function. Again, this is, when I say probability distribution function, this is also a density function. Okay, so that applies to the collection of fermions. Now, what are fermions? Fermions are half integer spins, particles with half integer spins. Not going into the fundamentals of this, most commonly known fermion is the electron. Protons and neutrons are also fermions. So when we have that, we have this particular function where I have this function called the Fermi-Dirac distribution function. So this is the Fermi-Dirac distribution function, or alternatively just the Fermi function. And so this gives me some value f of E. Now what is f of E? F of E tells me the probability of finding an electron between energies E and E plus D. Okay. So f of E is the probability density function. Now, by now, we should know what probability density functions are. So I'm not going to go too much into this. Now, the quantity mu, or some notations it's written as EF, it's called the chemical potential or the Fermi level of the system. So what does, and there are a bunch of definitions for this quantity. Now, this probability density that we are considering, like what does it depend on? It depends on the temperature. Now, if I'm having my collection of electrons, a very large number of electrons at a certain temperature, then f of E gives me the probability of finding electrons with energy between E and E plus D. And I need to integrate over a range of energies to get the probability of finding electrons in that window. Okay, so let us say I am having my system at 0 Kelvin. So what does 0 Kelvin mean? When I mean 0 Kelvin, I mean no inherent kinetic energy. Essentially, there is no thermal motion. I hope you know what thermal motion is. Like whenever there is some heat, molecules or particles will acquire some kinetic energy and they will start moving around. at 0 Kelvin, this kinetic energy is no longer available. Kinetic energy. However, we know that due to Pauli's exclusion principle, two electrons cannot have all quantum, essentially they cannot exist in the same state. So, well, if I include the spin, then no more than two electrons can exist in the same state. So what will happen is, even with in the absence of any thermal energy, the electrons will start occupying higher and higher and higher energy levels. So there is nothing supplying this energy to them. Just because of quantum mechanics, essentially their own intrinsic quantum fluctuations, they will gain more and more and more energy. And the Fermi level is the highest energy level occupied by a collection of electrons. When I say a system, so previously when we were talking about a quantum system, we were talking about a single electron. But when I say a system here, this is a collection of electrons. So this is a statistical, like, this is something that comes from statistical physics. Electrons. Okay, now alternatively, so at 0 Kelvin, we need to, like the electrons will start occupying higher and higher and higher energy levels up to the Fermi level. So essentially, if I have multiple electrons, let us say I have energy states something like this, then at t equal to 0, the first electron will occupy this, the second electron will also occupy this level, third, fourth, fifth, sixth. Let me say I have only 6 electrons. Then this energy level will be my, so for a collection of 6 electrons. System of 6 electrons. So this point, the highest occupied energy level is going to be the Fermi energy. Alternatively, we can also define it as the minimum energy a fermion needs to have to enter this collection. Now, let me say I want to add a seventh electron to the system. I cannot add them to any of these levels because these are all fully filled. Okay, here T is equal to 0. So the minimum energy is going, I need to have to introduce an electron is going to be, so let me say this is E1, E2, E3, and E4. I need to give at least E4 amount of, the electron needs to have at least E4 amount of energy to enter the system. So depending on our circumstance, we will have two definitions. The second definition is the lowest energy I need for my electron to get inserted into the system. And that is where this concept comes into play. So the chemical potential, so this is the definition of chemical potential. And where do we come across this term chemical potential? Like many of you may not have encountered it. So if you are interested, look up. So this is, introduced in the idea of a, introduced in the analysis of a grand canonical ensemble. So these are, ideas from statistical physics, not required for this course, but just for the sake of information, I'm leaving this here. Canonical ensemble. Okay. So come to problem 4. Now the question is, find the probability in percentage of finding an electron at an energy level 5 times kBt above the Fermi level of a system. So what we are told is E. So for part A. For now, we will stick to only solving problems directly. We will have a more detailed discussion in the Fermi level once we start doing the transport properties of an electron. So question 1, E is given to be EF plus 5 kBt, which implies E minus EF is 5 kBt, where Kb is the Boltzmann constant. It's just 1 and no, I think there are 2 n's. Yes, I think there are 2 n's. So, which implies just substituting it into this formula, it is going to be f of a is going to be one divided by, well, I should have said probability density. It's not the exact probability. Okay, so 1 plus e to the power 5 kBt divided by kBt, which is going to be 1 by 1 plus e to the power 5, and e to the power 5 is a number less than 5, so you can just take this as 3 to the power 5, which is going to be 9 into 9 into 3, 243. So this is going to be something like 1 by 244. So this is approximately 1 by 244, and this will come out to be something like 0.66 or something like that. So, sorry, 0.066. Sorry. 66. So in percentage, this is 6.6%. So that is the probability density. Now, second question is, use the above comment on probability that an electron with energy level below Fermi can undergo excitation. Okay. So I did not discuss this. But, well, you know what? I will discuss this next week because I have not covered that part, and we are almost at the end of our time. I don't want to discuss in next session. I will come back to this question in the next session because we took a good amount of time in talking about the dimensionality of a system that we could not discuss Fermi direct statistics in detail. Okay. Yes. So now this is a question we can solve. So we are told that f of E is equal to 1 by 4 at a certain temperature. Now, question is, what is f of E if temperature is doubled? Now, this question might look complicated, but actually it is very straightforward. So at a certain temperature, I know, essentially I know 1 divided by 1 plus e to the power E minus EF by kBt is equal to 1 by 4. Since this is equal to 1 by 4, there is one thing that I can directly say. That implies if we do all the fraction, manipulation and things, I can directly say essentially take the reciprocal of this left hand side and right hand side and subtract by 1 e to the power minus e to the power e minus ef by kBt is equal to 3. Like that is what this implies, because if this is 3, this will become 1 by 1 plus 3, which is 1 by 4. Now when the temperature is doubled, what is going to happen? This quantity will become the square root of what it was, because t is in the denominator, which implies e to the power e minus ef by 2 kBt is equal to square root of 3, which implies f of e at 2 times the temperature. So let me say this is some temperature T naught. So this is at T naught. Okay, 2 T naught is just going to be 1 by 1 plus square root of 3. And let me quickly just calculate that. So this will come out to be approximately 0.37. So this was 0.25. So this tells us a very important thing about the Fermi distribution function is that as the temperature increases, f of E at like, okay, how should I put this? Yes. If f of E was less than 1, uh, yeah, I need to make a new slide. I will make one here, drag it down. So this is, let this be the final takeaway from today's discussion on the Fermi level, Fermi Dirac distribution. If f of E is less than 1 at, and f of E is always less than or equal to 1. Okay, so it cannot be greater than 1. So f of E, that can be seen from this quantity here, like this relation. It is 1 by 1 plus a positive quantity. The smallest possible value this quantity can have is 0. It's an exponential function. Like it is always positive. So the highest possible value f of E can have is 1. Lowest possible value is, of course, when this diverges to infinity, it is 0. So if f of E is less than 1 at a certain temperature, then increasing the temperature will do two things. Will will A, increase f of E. If E is greater than EF, B, it will decrease f of E if E is less than EF. What about E equals EF? Like I'm telling that if the temperature is increased, f of E will increase for E greater than EF. It will decrease for E less than EF. At E equal to EF, go back here, like mu is essentially equivalent to EF. E minus EF will be 0. So this quantity will become 1. Just it will directly become 1, and changing the temperature will have no effect on it. So at E equal to EF, f of EF is equal to half at every temperature, even at 0 Kelvin. So that is the other definition of the Fermi energy. It is the point at which the probability of finding an electron is going to be half at all temperatures. So I will stop today's session over here, and next week I shall begin from exactly this point and cover the subsequent week's sessions. So with that, I will end today's session. I thank you all for joining, and we shall meet again same time next week. Thank you.